Alright, so you can see this, this is kind of a note that somebody else took. This is a student's notes. And so they've gone through, and last time or some time ago when I taught this lesson up on a whiteboard or something like that, a student took these notes and I thought, you know what, rather than write all these words out again, this person has such nice handwriting, let's annotate their notes and follow along with them, okay? So I've got these different scenarios. Scenario one, I've got a car that's just on a flat road, and we just talked about that. Car on a flat road, only this one is just a car that's on a straight track. So this car on a straight track, if you go on a straight track, no funny business, but if I look at this car and it's driving away from me, and I could say these are my tail lights. If you like, this is an animation where it's driving away from me. But it's hard to tell that because it's paper. But if this car was driving away from me, would the normal force and the gravitational force accelerated upwards or downwards? Answer is no, right? So we would say, okay, well, F normal and Fg are going to be equal in magnitude to each other, and we could throw in some magnitude lines in there. So we're going to augment this person's note just a little bit, say that the magnitudes would be equal to each other. And so the force due to friction, and really, we could say force due to static friction, because we want to specify this person's not going to slide from side to side, would be equal to the coefficient of static friction times the magnitude of mg. And the only reason we'd care about that if there was like a crosswind or something like that. So if there was a cross breeze trying to blow the car off track, this happens in the winter during winter season, that coefficient of friction drops to almost zero, and a cross breeze can blow you off the road on the 401 as you drive into Kingston or Ottawa. And I've seen lots of taillights in the ditch. This is a thing. This is something that you actually would care about, even on a straight road. 401's a straight road. And people experience this. But it's a basic scenario. Scenario two, we keep a flat road, but a curved track. This is exactly what we talked about before. In this case, we would have Fc being the centripetal force. Remember, this is net force for circular motion. And that net force for circular motion would, at a minimum, have to be equal to the force due to friction. So I could say Fs specifically has got to be, really it's got to be greater than or equal to. But as we talked about before, using the equality lets us solve nicely, okay? So it's got to exceed the demand placed on it by the centripetal force to make the curve. Otherwise it's going to slip. And so we could go through and specify that this is static friction force, that this is mu s, that this is a magnitude of mass times acceleration due to gravity. But this is exactly what we just looked at. Now, if we were going to go through and solve a problem like this, this is one that's already solved out, and you can run the numbers yourself. The answer ends up being 52 meters per second. But this is exactly what I was just talking about. In a world where you already know what the coefficient of friction is, and you know the radius of curvature, you could know the mass of the car if you want to, but notice that the mass shows up in this equation. Call it equation 1, call this equation 2. But if I let 1 equal 2, you end up getting mv squared over r equals mu mg, and the m's drop out. Okay, and so again, this ends up becoming mass independent. And so if you are a civil engineer and you're trying to figure out what speed cars should be able to take a corner at for a given grippiness on the road, that's the static friction coefficient, and the given radius of curvature for a road, think like highway off-ramp or turning lane or whatever, you could calculate this, right? And so this is, again, a statistics game. Maybe you'd even want to not calculate it for the average coefficient of friction. Maybe the coefficient of friction that you want to use there is for bald tires. And if you really want to protect all the people out there, regardless of their car maintenance abilities, I might want to use radius of curvatures and speed suggestions that would match up with people that have coefficient of friction for bald tires. Because I just want to save lives. And yeah, it might make for some wider turns, and yeah, it might make for some extra gravel on the turns, but let's just not let people die, okay? And I would be willing to bet there are a lot of civil engineers out there that have made that decision. Poured a little extra gravel in the mix, you know? And we're cool with that. And the beautiful thing about this is, if you do your engineering right, nobody even knows. If you do this right, nobody will know that you saved their life. It's just invisible. It's in the background, right? And so that's the kind of thing that you want to be able to do. You want to be so smart that you design a world where everybody's safe. Right? And that's important for us. And that's not a question of bubble wrapping people. That's a question of just like recognizing that people have busy lives and they forget to change their tires and all that sort of thing. And we just don't want people to die. All right, next scenario. Scenario 3. This is one where we got a straight road, but it's called a banked road. This is an unfortunate road. And there actually is a road near here. If you go up Burloak, there's a road that's a little bit tilty. And actually, it's not so bad. But it's tilty on purpose. And it has to do with the fact that there was an old country road that was there that had a ditch beside it. And then they put in a new road, and underneath the new road, they put storm sewers. And so rather than having to have the two roads be exactly the same, it actually turns out that the northbound roads are at one level and the southbound roads are at another level. And honestly, I can't remember off the top of my head which one is which going up that road, up Burloak. I think it's the northbound roads that drain into a ditch and the southbound roads that drain into a storm drain. In any case, they slanted the road a little bit to make sure that the water goes towards the ditch. And that makes a lot of sense. Now, as far as I know, it doesn't cause any accidents, but in an extreme scenario, if it was really banked like this, can you imagine that roads would get sort of pushed off the road into the ditch? So like if the ditch was right here, yeah, the water would run off. Yes, you'd get less black ice in the winter, but you'd get some more roads in the ditch. And as far as I know, that road is not so heavily banked that that's a problem. But that's the sort of thing to look out for. Maybe you'll notice it the next time you drive up there. But road is tilted at an angle theta, but runs in a straight line. And what we end up getting is that since gravity is pulling down, we've talked about this with ramps, with inclined planes, you would end up having an FG perpendicular and an FG parallel. FG perpendicular pulls into the road, and we say that it contributes to F normal. And FG parallel is pulling down the hill. So into the ditch, if you like, which is desirable for water, less desirable for cars. Okay? And I could make the little comment that this is just like ramps. Now keep in mind again, and this is a hard thing for people to remember sometimes, is that it's not a ramp though. This is an animation. This is a car. Look, there's the car's taillights. It's driving away from us. In animation, this is just a snapshot of a car that's in motion. It happens to be in motion away from us, and while it's driving away from us, gravity is trying to pull it off path. And if you are on a road like this, you do have to battle it. One time I was in Oregon, and I was driving through the mountains in Oregon, west coast of the U.S., and I said to the missus, I said, this is beautiful. It would make this even more beautiful if there was a little rainstorm. And then the clouds opened up, and it rained! I was like, oh my gosh. I'm like, me and Thor, like commanding the weather. And then, I know you look at me and you think Thor, right? But don't pull that face. I saw it. So the rain comes down. And the thing is, it's tilted like this because it's a banked road in the mountains, not because it's a design, but because the cliff's falling away. And so there I am, like, terrified now because the road is wet and I'm about to fall into the ocean. And then I was like, what would make this worse? Is if it was hailing or snowing. And then honestly, I felt like very deified in the moment. It started hailing. And it was terrifying. And then Mrs. Killen's like, the icing on the cake would be lightning. And I said, shut up, and then it lightened. And it was amazing. Honestly, it was like the most terrifying, beautiful experience ever, as I almost died falling off this road. Not by design, though. Definitely because the cliffside was falling away. And it was totally beautiful. Like, the rain cleared up after that, right? And then, the angelic sun came down as a shaft of light, and I was like, wow, this is the time. I feel like I should, step out and walk on water or something just to test it or something. But it didn't happen. Anyway, force due to friction. This static friction force has got to be greater than FG parallel. Otherwise, what's the car going to do? Slip off the road. And in the case of my Oregon trail, I would have died. But in the case of a more local situation, we want to make sure that we don't just slip off into the ditch, right? And we do have roads like this, and drainage is the reason, usually. Okay, so we still are mindful of it, and people got to make sure those guys get shored up. And when I say greater than or equal to, let's just make the commentary in order to not slide sideways. And in this picture, sideways would mean going down the ramp, because remember, this is an animation where we're driving away from the camera, if you like. And if I was going to do a calculation on this one, I could set up a formula for myself where, yeah, we know that for ramps, F normal is FG perpendicular times mass times acceleration due to gravity times cosine theta. We've been there. We've done that. We know that the normal force is equal in magnitude to that value. We know that this friction force that must not be exceeded by BFG parallel would have to be greater than or equal to mg sine theta. And so we could calculate what the coefficient of friction would be. But again, something interesting happens. Notice that there's a mass on both sides, and so we can cancel out the mass. And then something even better happens. We even cancel out gravity. And then something even better happens, and I get like, I don't know, like the tingles. Look at this, sine theta divided by cosine theta, tan theta. You're like, holy smoke! If you're on a straight road, the coefficient of static friction, mu s, has to be greater than tan theta for that banked straight road. That's all we need to keep us on the road and not slide sideways. And so if you wanted to use the coefficient of static friction for bald tires, you could just make sure none of your roads exceed a banking angle that obeys bald tires. And so that should be our, while I don't work in any standards industry or anything like that, I'm a high school teacher. I think if I was setting standards, that would be my standard. Driving on straight roads with bald tires. In the winter, on ice. I don't want to exceed that, because don't want to kill anybody. So I'm not even going to plug any numbers into that, because I feel like we can handle it. But there's more. Because if there's a banked road that's flat, there surely is a banked road that's curved. Okay, why not? So now we've got a car that's going to be on a banked road, but this banked road is taking a corner. And it's hard to picture this if you're not super keen on in-your-brain animations. But here, how about this? What if I draw an ellipse, and I think to myself, that could be the road, except it's like a bowl, but I'm not going to finish the bowl. I'm just going to like flatten off the bowl, kind of like a frying pan. And then I'm going to wrap around in the background. I say, yes, a banked curve on like a racetrack or something like that would be like if I could just cut off the top, inch of a tapered frying pan, there'd be that banked curve. And that's what we're talking about here. We're talking about a car that can drive away from us. Look, this is the zoomed out version up above of this car that's on a track. And right in here, there's the tail lights as it drives away from me. And if I were to take that car and blow it up to this picture right here, I'll say like a bowl. When I was a kid, I can distinctly remember grabbing my mom's metal mixing bowl and taking a car like this one and just doing almost like a hula hoop motion with the mixing bowl and getting the car to drive along the banked curve on that mixing bowl. And you think like, oh, you should have had better toys. But I'm telling you, it was a good toy. And actually, try it. Grab a mixing bowl, grab yourself a Hot Wheels car or something, and do like a hula hoop motion. See if you can get it to drive these inside of that bowl. It's going to be a banked curve like this. It's actually, there's a limit to how fast you can hula hoop with this thing to get it to zing around the inside of the bowl. It's kind of like a neat kinesthetic exercise. And no, I don't have like a class set of mixing bowls to hand out to people, but try it out. It's neat. You can do it with a marble too. It doesn't really matter what the object is as long as it rolls. But you get like this idea of the forces that we're talking about, okay? So what we've got is a gravitational force that's downward, Yep, no doubt about that. We've got a normal force that's perpendicular to the contact surface, but we actually go in a slightly different direction with this. What we say this time is, this thing's an animation. It's trying to go into the page. Remember, I've been pushing this idea. These are taillights. It's going away from us, right? It's driving into the page. But it's not just driving into the page anymore. It's driving into the page and turning a corner. It's doing both of those things simultaneously. And so something has to cause it to turn the corner. And we already established that that means there's got to be an inward force. And if I look at this, well, gravity is not giving me an inward force. Agreed? That's a downwards force. So I got to think about the normal force. The normal force is a real force. It's not just like an academic construct or something like that. It's a force that pushes the car, right? But when I look at this, I think, wait a minute, it's got an x component. And I know that we've broken it up into perpendicular and parallel components before, but we could just as validly break it up into x components and y components. And in this moment, I want to declare that that x component would contribute to the centripetal force, wouldn't it? Gravity doesn't. There's nothing else here. So it must be this. And then that begs the question, what about this y force? Well, in this context, if the x component is contributing to the centripetal force, then the y force is actually just what's doing battle with gravity and keeping it from falling. That's all. And so sort of in a weird turn of events, that upwards component there is now dealing with gravity, kind of like we might have thought about things sitting on level ground, because we don't want our car to go up or down the ramp, up or down the bank. We want it to stay at the same height on the bank so that we can take a curve. And so the x component is going to be the centripetal force component. So let's just make sure we hash out the words that are already written. So gravity pulls down with a force of Fg equals mg. Agreed. In order to keep the car from falling through the surface, the road must push straight up with an equal force. That's the y component. So I'm going to call this F normal y. And I'm going to label it over here, F normal acting in the y direction. And that F normal acting in the y direction has to be equal to the Fg value. Everybody cool with that idea? All right. And you know what? I think I want it. That's so important. I'm going to put a box around it. And at the same time, I already touched on this, there's this x component. Well, it turns out, and you can actually talk about how I know that this angle is what it is. But you know, hey, maybe I'll go back to this diagram up here to make a mess of this one. If I extend that normal force backwards, we said on ramps, remember this angle here was the angle of incline of the ramp? Can I point out that by opposite angle theorem, this angle here is the angle of incline of the ramp, but also this angle here is the same angle. Okay? So we went through an angle proof to explain why these two angles are the same. This is an even easier angle proof to say that by opposite angle theorem, those two angles are the same. Okay? So I'm going to come, with that in mind, I'm going to come back down here to just say, hey, look, that theta and that theta are the same by that logic, okay? Now I can say, okay, well, if I want to know the y component of that normal force, I'd say that F normal sine theta, there's theta, is going to be equal to Fc at a minimum. I'll just say at a minimum. Okay? And I could write underneath of this, because there's a little bit more real estate down here, I could say F normal in the x direction. And over here, I'll call it F normal in the x direction. It's going to be that F normal sine theta. I'll put a box around that one because it's important too. So of the scenarios, the scenario 4 seems like it's the meatiest. You know, it's like got the most dense information. And I come down here, and I say, okay, to keep the car from falling through the road surface, I want to say F normal cos theta has got to be equal to gravity. I know I already said that out loud, but this is my y thinking. F normal cos theta has got to be equal to force due to gravity. That's going to keep it from falling, which means that F normal, if I rearrange, could be isolated to be mg cos theta. Now I want to call this one my equation 1 for this page. Now in the absence of friction, if this was a frictionless, notice I haven't brought up friction yet, right? In the absence of friction, the only force contributing to centripetal force would be the normal force, the x component of the normal force. And so I could say, okay, well, F normal sine theta is equal to mv squared over r. That's the x component of the normal force contributing to the centripetal force. And again, if I isolate for the normal force, I end up getting F normal equals mv squared over r sine theta. I'm going to call that one my equation 2. Then I want to say, let equation 1 equal equation 2. And if I let equation 1 equal equation 2, I get an expression like this. Immediately, I say, well, okay, so for a banked curve with no friction, I could make the curve if those two equations are equal to each other. And I say, masses, be gone, because they cancel out. And that's nice. This is the power of the generalized equation. Sine theta, I'm going to take you up to the other side. So now I have sine theta over cos theta. G, I'm going to bring you down to the other side. And the reason that I would do that is so that I can recognize by that basic trig identity that I've got tan theta sitting over there on the right-hand side. You know, we kind of did this once before with something similar. And I got v squared over gr. Again, the nice thing about this is that an equation like this is for no friction considered. So this is a frictionless scenario. On a banked curve. That would be the relationship between the speed I could go, the radius of curvature, and the banking angle with no friction. And people say, well, why would you want to have that cute little equation? Well, that cute little equation there would allow us to decide what the radius of curvature and the banking angle would have to be in black ice conditions. Basically when there's no friction at all. And again, from like an engineering perspective, from a road design perspective, that would be valuable, right? I would like to know how I can make things safe in the extreme scenario. If there's an oil spill, could cars not fly off the road? Yeah, this is good stuff, right? So this is, I know, kind of a basic, people will say not real life because there's no friction, and everybody knows there's almost always friction. But that's your extreme scenario. And so sometimes people want to know the extreme scenario for how we want to bank a curve. You can imagine this might be something you'd think about if you were banking for competitive race car drivers or something like that. You want to make sure that you could design a curve so that if the wheels totally melt down at high speeds on the Indy, less people die. Important stuff. Right? All right, I'm going to pause there for a second.